Time may or may not be real, but whatever your philosophical position on the matter may be, what is certainly real is our ability to measure duration. It doesn't rely on the sun, and it doesn't rely on anything that humans invented. Curiously, it relies on caesium. See, all of the things that humans make are imperfect. The mechanical clocks of the second millennium were a marvel for their time, but even by the 1700s, the best clock of the time lost 5 seconds after only 10 weeks. That may not seem like much, but if you're a scientist doing experiments over the course of weeks, that level of precision is unacceptable. Furthermore, these kinds of timekeeping devices aren't universal, meaning that the length of a second, as measured by such a clock, depends on the build quality and specifications of the device. And that's also unacceptable. It means that no two devices measure the same second, so measured durations will depend on who is measuring them. So, if we want accuracy and universality, what can we do? Well, a first guess might be to use something every human can experience, the length of a day. In 1862, it was declared that a second was defined in the normal way so that there are exactly 24 hours in an average day. And this is pretty good. After all, it's globally measurable and verifiable, so you can always correct your clocks if needed. But there are some issues with using the Earth. The average length of a day changes. Every century, a day gets approximately 2 milliseconds shorter, and on a smaller timescale, large earthquakes can permanently change the length of a day by a few microseconds. And that means that while the length of a day is effectively spatially universal, it's not temporally universal. You couldn't use it to compare durations across time. Now, for a while, the average length of a year has been known to be more stable than the length of a day, but it's still not good enough. And what if we eventually travel to the stars? Any standard that depends on nearby measurements cannot even in principle be truly universal. Enter stage right, the atomic clock. As far as we can tell, the laws of physics are the same everywhere in the universe, and they're unchanging throughout time. And so we can use physics itself to set the standard for time. Since 1967, we've defined the second based on a certain property of a particular isotope of caesium, caesium-133. Electrons around an atom have well-defined energy levels. You might remember the picture of an atom with electron orbits from high school. Those orbits represent energy levels. Now, because electrons can absorb or emit photons, and they can only occupy the energy levels allowed by the atomic structure, any emitted photons can only take on very specific values of energy, and hence very specific frequencies, as photon frequency is proportional to energy. So what did the physicists do? Well, they looked for atoms with as few confounding factors as possible to measure these frequencies. First, the atom should have only one stable isotope, so they don't have to purify the substance. Next, it should turn into a gas at low temperatures so that it's easy to treat it as an individual atom, but not so high temperatures so that we have to worry about the Doppler effect. Also, the atom should have an intrinsic nuclear magnetic field so that we can measure energy levels resulting from spin flips of the electron, a so-called hyperfine transition. This is the preferred type of transition to measure because it means the excited states can be filtered out with an externally applied magnetic field. If you put all of those requirements together, you'll find that caesium-133 is basically the best option. Then it's just a matter of bombarding a caesium gas with microwaves and tuning the frequency of the microwaves until you see a peak in the number of excited atoms. Finally, we can define a second to be exactly the amount of time it takes for that peak microwave frequency to go through 9,192,631,700 cycles. And that's a truly universal definition regardless of when or where you are in spacetime. Timekeeping devices, but we don't want it to be a gas that's such. Next, it should turn into churn microwaves and turning the frequency 631.7.